Hello and welcome to another lecture on EPO 640 electric drive. Okay, so for today we will be discussing on DC drive, okay, part 1. And for DC drive, we will look into review of a DC motor principle. And okay, so for this topic we have I've put it into 4 to 5 parts. Okay, so for part 1 we will look into the review of DC motor principle. So DC motor introduction. Okay, so the direct current or DC machine can be used as a motor or generator. And the major advantages of DC machines are the easy speed and torque regulation. However, the application is typically limited to mills, mines, and trains. As examples, for trolleys and the underground subway cars may use DC motors. And in the past, automobiles were equipped with DC dynamos to charge their batteries. And even today, the starter is a series DC motor. However, the recent development of power electronics has reduced the use of the DC motors and generators. The electronically controlled AC drives are gradually replacing the DC motor drives in factories. And nevertheless, a large number of DC motors are still used by industry, and several thousands are sold annually. Okay, so for DC motor, so one of the revisions that you can look into is the Lorentz law. Okay, so you can further Google, or you can search in your textbook on the Lorentz law. Okay. And also please revise on the left hand rule. Okay, so you have the motion, field, and current direction for this. And please revise on this topic also. And based on the Lorentz law and the left hand rule, so you have the motor construction for the DC motor. Okay, so you have carbon brushes connected to your commutator. This allows the force to be unidirectional with the commutators, so that you can maintain one flow for your current. Okay. Okay, so next we look into the DC motor construction. Okay, so the stator of the DC motor has poles. Okay, so here you have poles which are excited by the DC current to produce magnetic fields. Okay, so in the neutral zone in the middle between the poles, commutating poles are placed. Okay, commutating poles are placed to reduce sparking of the commutator. The commutating poles are supplied by the DC current. So compensating windings are mounted on the main poles. Okay, these short circuit windings damp the rotor oscillations. And the poles are mounted on an iron core that provides a closed magnetic circuit. And the motor housing supports the iron core, the brushes, and the bearings. Okay. So the rotor has a ring-shaped laminated iron core with slots, and coils with several turns are placed in the slots. So the distance between the two legs of the coil is about 180 degrees. And the coils are connected in series through the commutator segment, and the end of each coil are connected to a commutator segment. So the commutator consists of an insulated copper segment mounted on a insulation tube. So two brushes are pressed to the commutator to permit current flow, and the brushes are placed in the neutral zone where the magnetic field is close to zero to reduce arcing. And the commutator switch the current from one rotor coil to the adjacent coil, okay, and the switching requires the interruption of the coil current. So the sudden interruption of an inductive current generates high voltages, and the high voltage produce flashovers and arcing between the commutator segment and the brush. So in a DC motor, the stator poles are supplied by DC excitation current, which produces a DC magnetic field, and the rotor is supplied by DC current through the brushes, commutator and coils. And the interaction of the magnetic field and rotor current generates a force that drives the motor. So here's some classification of DC motor. So for this section, we will discuss three types of motor. Okay, the first one will be the separately excited, okay, and shunt motors. Okay, next will be the series motors and the compound motors. So first, the separately excited or shunt motors. So field and armature windings are either connected, okay, separate or in parallel. So for the separately excited, it's separately connected, and for shunt motors, it's connected in parallel. And it provides full torque even at almost zero speed, but the separate field supply adds cost and complexity to the system. It runs at approximately at a constant speed, determined by the applied voltage as the load changes. Okay, so that's for separately excited and shunt motors. So for series motor, the field and armature windings are connected in series. Specially constructed motor with field windings in series with armature, and field windings only has a few turns as it takes the full load current. And torque speed characteristics are similar to the constant power. And for the third one, the compound motor, it has both shunt and series field, so it combines features of a series and shunt motor, so both. So here is the diagram of the separately excited motor. So at the upper part is the field part, okay, field connection, a direct connection to the power source here. So you have LF and RF, one loop here, and the below diagram is the armature circuit. Okay, so you have your okay, input DC, okay, connected to LA, RA to the rotor, okay, armature. So you have your field and your armature are controlled separately. Okay, so the armature winding supplies to the load, okay, and the field winding is supplied by separate DC source where the voltage is variable. So in that case, you have a very good speed control. And okay, so on the right you can see the shunt connected DC motor where you have your your field circuit and your armature circuit is connected in parallel. Okay, so you only have one source compared to separately excited here. So here you have only one source. Okay, and for that you have your armature voltage and field voltage is the same, and the input current is equal to IA plus IF. And for a series DC motor, so you have your field and your armature circuit in series, okay, connected in series. So armature voltage, okay, input voltage equals to armature voltage plus field voltage, and you have your input current I in is equal to IA and IF. So let's look at the application. So usually for shunt motors, okay, for constant speeds stay relatively constant from no load to full load. Okay, there is a good good speed regulation. Okay, so usually used in a centrifugal pump, okay, machine tools, blower fans, okay, pumps, etc. Okay. So next you have the series motor, which applications require high starting torque or high speed at light loads. Okay, so it has good acceleration due to high torque at low speeds, and on applications such as electric trains, okay, cranes, hoists, elevators, and etc. So the separately excited DC motor, it separates supplies from the stator and rotor circuits. The armature is accessed by a commutator, which ensures that the current flow in the winding is orthogonal to the flux. Okay, so you can see that torque equals to, okay, the constant K times flux times the armature current. Okay, so it follows the Faraday law and the left hand rule. So let's look into the equivalent circuit. Okay, so the field winding is used to excite the field flux. Okay, field winding, and the armature current is supplied to the rotor, okay, through the brushes and commutator, and the interaction of field flux in the armature current in the rotor, okay, produce the torque. Okay, and you can see all the labels here that we have, okay, in order for us to make the equivalent circuit. So first we look into the torque developed by the motor. Okay, so torque equals to, okay, KT IF IA, okay, or torque developed equals to KT, okay, flux IA. Okay, so you can see the value of KT. Sometimes it use the value of KT, or it's actually equivalent to KV. Okay, so later on we will look into the constant for kVA. So for normal operation, the developed torque must be equal to the load, okay, torque plus the friction and inertia, okay, within this equation. Okay, so you have what is B is viscous friction constant, okay, in Newton meter per rad per second. Okay, and then you have TL, okay, that is the load torque, and also J is the inertia of the motor. Okay, then we look into the instantaneous field current, okay, VF. Okay, so VF, okay, voltage F is equivalent to this equation. Okay, so you have your RF is the field resistor and LF is the field inductor. Also on the instantaneous armature current, okay, VA. So VA is the voltage armature, RA, IA, LA, okay, within this equation. So you have Ra is the field resistor and La is the field inductor. And also you have the motor back EMF, okay, the armature back EMF, which is also known as a speed voltage, okay, given by E equals to kV omega IF. Okay, so omega is the motor speed, okay, and kV is the motor constant, motor voltage constant. And during steady state operation, okay, so time derivatives are 0. So assuming that the motor is not saturated, you can say that Vf equals to IFRF. Okay, so for the back EMF, okay, Eg equals to kV omega IF. And also for the armature circuit, Va equals to Ra Ia plus Eg, or Ra Ia plus kV omega IF. Okay, so this is for steady state operation. And you can easily derive the speed also. Okay, so from the three equations earlier, so you can derive the speed, okay, omega. Okay, and if Ra is a very small value, okay, within is usually the case where Ra is very small, the resistance is very small in the armature circuit. So when the motor is highly loaded, okay, Ia is very small. So we can say that, okay, omega, okay, is equals to Va out of kVIF. So if the field current is kept constant, the motor speed depends only on the supply voltage. Okay, so you can derive the torque Td within this equation, and the required power will be this equation. So bear in mind, this will be during this steady state torque and speed. So from the derivation, so several important facts can be deduced for steady state operation of DC motor. So for a fixed field current, okay, or flux, the torque demand can be satisfied by varying the armature current, that is the Ia. And the motor speed can be varied by one, controlling Va, or we call it the voltage control, and number two, controlling the Vf, or we call it the field control. So this observation leads to the application of a variable DC voltage to control the speed and torque of the DC motor. So the family of steady state torque speed curve for a range of armature voltage can be drawn as here below. Okay, so the speed of the DC motor can simply be set by applying the correct voltage. So for this example, you have, okay, so your speed reference, okay, 250 RPM, 500 RPM, up into 1000 RPM, with a different, okay, rated voltage. Okay, so in this case, for 250 RPM, you have 125 volt. Okay, and for 750 RPM, the requirement is 375 volt, for example. Okay, and all these have a rated torque. Okay, so these are within the rated torque. Okay, so the speed of the DC motor can simply be set by applying that correct voltage. And note that the speed variation from no load, okay, no load to full load, okay, can be quite small. Okay, so it depends on the armature resistance. So you can see for the first example, so for during no load, okay, so if your torque is 0, no load, so you see that the speed is much higher than, okay, much higher than if you apply for rated torque, for rated load, okay, here. So it has a slightly higher speed during no load, okay, but not that obvious, okay. So but then it depends on the armature resistance, okay. So if your armature resistance RA is high, so you can see the difference will be higher, okay, here. Okay, and also you have your base speed and field weakening, okay. So base speed, what is base speed? Okay, omega base. Okay, so the speed which corresponds to the rated VA, rated IA, and rated IF. So here, for example, this is speed. Okay, speed. Maybe this is speed to voltage here. Sorry, speed to torque. Okay, speed to torque or speed to power. Okay, so this will be the base speed region, okay. So it will follow uh, the correspondent rated VA, rated IA, and rated IF here. So constant torque region, so where you have your omega is lower, okay, even or lower than the omega base, okay. So IA and IF are maintained constant to meet torque demand, okay. And VA is varied to control the speed, okay. So here you have your power, it increases within the speed, so it's very easy to regulate it in this case, okay. And then you have another region where you have a constant power region. So omega is, okay, your speed omega is higher than the base speed. So in this case the VA is maintained at the rated value and IF is reduced. Okay, IF is reduced to increase speed. Okay, so here we call the field weakening. IF is reduced. So however, the power developed by the motor, okay, that is the torque times speed remains constant, whereas you see your torque is reduced. Okay, so this is known as the field weakening. Okay, so in cases where you want to increase your motor speed, but you have reached your base speed, but you want to further increase your motor speed, okay, you can opt to reduce your IF, okay, but then your torque will be reduced and you have a constant power, okay. So again we look into the 4-quadrant operation, okay. So we have done this, okay, previously. You can see the in this case the x-axis is speed and y-axis is torque, okay. And for the A region, or number 1 region, is forward motoring, and then you have reverse generating, okay, or you can call it a reverse braking, braking, forward braking or reverse generating. So this one, number 3 will be reverse motoring, okay. And number 2 here is forward generating, or sometimes it's called the uh reverse braking, okay. But then it depends on your axis, okay. Sometimes your speed can be at the y-axis and your torque can be at the x-axis, okay. So different textbook, they have different references, and you have to be careful on this, okay. So for regenerative braking, that is in Q2, okay. So say the motor running at position A and suddenly VA is reduced, okay, to below armature EG, okay, below the value of EG. So the current IA will be in a reverse direction. So operating point is shifted to B. Okay. So since IA is negative, okay, torque is negative, power is also negative, which implies power is generated back to the supply. And in other words, during the deceleration phase, kinetic energy from the motor and load inertia is returned to the supply. And this is known as a regenerative braking. Okay, an efficient way to brake a motor, and it's widely employed in electrical vehicles and electric trains. Okay, and if we wish the motor to operate continuously at position B, so the machine have to be driven by a mechanical source. So the mechanical source is called the prime mover, and we must force the prime mover to run faster so that the generated EG will be greater than VA. Okay. Okay, so then we look into other drive types that we will cover in the following lecture. Okay, so you have the SCR, that is the phase angle control drive. Okay, so this is done by changing the firing angle. The variable DC output voltage can be obtained. And also you have the single phase or three phase supply, okay, that can be used. And the line current is unidirectional, but the output voltage can reverse polarity. Okay, so hence you have a two quadrant operation is inherently possible. So for the four quadrant is also possible by using two sets of controlled rectifiers, or you can also opt to a switch mode drive, okay, using switch mode DC-DC converter, and DC voltage is varied by the duty cycle. Okay, so it's mainly used for low to medium power range. Okay, so as you have learned this in the power electronic subject, you have the single quadrant converter, okay, using a buck converter, that will be referred to as a one quadrant drive. Okay, so for a half bridge drive, it's for a two quadrant drive, and for a full bridge drive, you have to operate a four quadrant operation. Okay. And also this you can refer it to the internet. Okay, the earlier variable speed drive, using a Ward-Leonard system, where to control a motor you are using another motor to control a motor. So you have your your motor, your load here will be the motor here, and also you have a generator here. Okay, so you will control the generator to control the load here. Okay, so this you can refer to the internet for the Ward-Leonard system. Okay, so this will be the conclusion for part 1. Okay, thank you, and hopefully you can stay safe, and please answer the quizzes that will be posted. Okay, so by this, thank you.